I don't think you mind, David, right?
I don't mind, no.
All right.
I've been recording myself presenting stuff for a long time when I was in the previous employee with ANSYS, right? Everything I did was recorded. So if you go on YouTube, you can search for video.
That's something to say. David is the most prolific YouTuber regarding ANSYS and electromagnetics. If you go into YouTube and look for ANSYS electromagnetics, David is going to have hundreds of videos. Yeah, and he is explaining everything there. But that is for ANSYS, not for
but at the end, I like COMSOL better. So I have the experience with both, and like I say, I can tell you why I like COMSOL better and why it is, right? But let's start with the solver settings, right? What you see in the solver settings and the default settings that are applied is based on the physics that are in the model, right? So here I have a heat transfer module, surface radiation, laminar flow. Based on these physics and also the multi-physics, that's what appears here in the physics interface and the multi-physics coupling, right? And based on these physics.
Are you opening windows? Because the windows are not being opened. We only see your simulation, your heat transfer simulation.
Exactly. Exactly. Yeah. I'm just, but you see the cursor, right?
No, we don't.
What do you see? You see what do you see in the screen?
We see the console figure and we see the heat transfer going on. So the temperature is increasing.
Okay. I need to show a different screen then. Hold on a second.
Yeah, we're seeing your other screen.
Okay, hold on a second. So I guess it's this one. Hold on, let me see. Is this the one you see now, the settings?
Okay, now we see a different one. Yes. Very good.
Wait, hold on a second. PR. I got different ones. Okay, this is the one I want to show. Okay, now you see the settings, right?
Well, how many screens do you have, David?
Multiple. But now you see my cursor?
Yes. Now
okay.
I see
okay. So you see here physics interface, right? Heat transfer in solids, surface radiation, laminar flow. And I got coupling with laminar flow and heat transfer surface radiation, right? So depending on the physics that you have in the model, that's what you see in the physics interface, right? And that what determines the default values for relative tolerance. In this case, I'm using time-dependent solver, right? So before anything, you have to choose the solver. Once you have the physics here, you go to study. You can right-click on study, or you can, if you don't have a study, you go to the ribbon on top, study, and then you add a study. And you could, like, once you click this, you could choose what study to add. Typically, I use time-dependent study because I do a lot of transient analysis, time-dependent.
Let's do the stationary.
Okay, so if I just click stationary.
And which methods, the solution methods are opened?
Okay, so I add the study, right? And then once I add the study, so now I have two studies. I originally had a study with the time-dependent solver, and now I'm adding a separate study, stationary, but it has no solver settings, so I need to apply the solver settings. So I right-click study, and I click show default solver. So now I add the study, but I have to add the solver for the study, right? I click this. It loads up, and then it's gonna have the default settings. So if I click stationary, it's gonna show the physics that I have, right? The 3 physics modules, the 2 couplings, and we have different drop-down like boxes here, right? But really what we need to focus on is the stationary. So if we want to like turn off some of the physics, we could uncheck some of them. Let's say we want to troubleshoot. Let's say we have a simulation that's very complicated and we want to know which physics is the one causing the problems with convergence, right? In this case, a lot of times this is like laminar flow. See, convection is very complicated, right? So I could turn off laminar flow, and I would see that the heat transfer and solid surface radiation converges easy, right? Then I know for sure, okay, it's definitely laminar flow that's complicated, right? So you could uncheck one by one, and you could troubleshoot and narrow down which physics you need to modify or to facilitate the convergence, right? You may have to update the mesh, you may have to adjust, for example, see each solver, they have options for relative tolerance. So you may have to adjust this. Now, the accuracy of the solution depends on relative tolerance. You don't want to make this too small, right? It's good to leave it default or make it smaller. I don't make it larger, right? So leave it as it is, or you make it smaller. That's what I do.
The relative tolerance refers to what?
So the error between solutions at different iterations, right?
I see. So when the previous solution varies, whatever it is,
whatever, exactly, yeah,
less than 0.001, it converges.
exactly, yeah. So you could, we could control how tight you want the tolerance to be. So in this case, that's one tolerance value to look at, right? And then
okay, so let's go to segregated and
yeah, exactly. So segregated solver is one of the solvers that COMSOL offers, in addition to multi-physics fully coupled solver, right? The fully coupled solver solves all the physics simultaneously, and the segregated solver solves it independently and then merges the solution, right? And by default, it's using this one, segregated solver, by default, but I don't have to use this. If I want to, I can right-click stationary solver, and I can add fully coupled solver, right?
If you have a single physics, what would be the case? What would be?
It depends. Like if it's simple physics,
say
fully coupled,
electromagnetics, frequency domain, what would be the solvers available there?
Both of them are, all of them are available. You could choose, but it like you have the option for to leave it default. Like sometimes segregated default, sometimes fully coupled default.
But let's say a frequency domain case, an AC/DC eddy current effect problem.
So what would be? Oh, what you're asking me?
What would be the recommendation for that comes from COMSOL, and what would be your recommendation?
I always use fully coupled. Although this is what COMSOL told me. COMSOL told me, when I communicate with them, that it's good to leave the default settings, right? The settings, the solvers are designed to work best with the physics in your model, right? But fully coupled solver, it may be a little more difficult to converge because you're trying to solve everything at once, right? Or like I got in this case 3 physics, heat transfer, convection, right? Surface radiation. So it may be more challenging, but segregated solver is supposed to be for models that are considered complicated. Going with the segregated solver is supposed to be like easier to converge, but I still like fully coupled because it's that's what it means. Fully coupled means it's tight coupling. So if you have like induced like eddy currents, right, stuff like that, coupling like electromagnetics with thermal or something like that, like different physics, I like to use fully coupled. Like it depends too, like how maybe put it like this, maybe it's good to start with a segregated. Once you have the insight of the simulation and you see the results using the segregated solver, it's easy to converge. At the end, you can always say, okay, for the final results, I want to use fully coupled, right? You could do that. But I don't know from the top of my head for any simulation, given simulation, what answer is going to recommend from the top of my head. I don't know. And it also depends too if it's a 2D model or 3D model. Now it may be for a 2D model, COMSOL may use fully coupled. But for 3D models, much more complicated, is gonna most likely go with a segregated model. So it depends on the dimensions, 2D versus 3D, complexity, all the different.
So recommendation number one is try first the default.
Yeah, try the default. Yeah.
Okay. What happens if it doesn't converge? What is your next process? Let's say let's talk about an electromagnetic eddy current problem. You have a motor, your motor design, let's say the motor from Nader, something like that. So you will build the model, 2D model, simple, say a transformer, right? Say a
So you're saying
transformer,
stationary or time dependent?
stationary.
Okay,
Let's
stationary.
start
So
with stationary.
the first thing I do before anything is the mesh, because the solver is not going to tell you if you have a good mesh. It's
Okay.
your job to build a mesh, to analyze it,
All right.
and then use a solver, right? Because
All
if
right.
you have a bad
Tell,
solver, the solver
tell,
is not going to tell
tell us
you.
about the mesh. Tell us about the mesh.
Okay, so so we could start with, this is what I do. So right now I'm using, you have two options: user controlled mesh or physics controlled mesh, right? A user controlled mesh is a custom mesh. You have total control of how to build the different mesh elements, right? So in this case, I want to, this is a 3 trefoil cable, right? 3 single core cables arranged in trefoil, right? And we have convection heat transfer, right? So it's fluid flow. So I need to design the boundary mesh layers. So in this case, I got 5 layers with a stretching factor of 1.2, which means each layer larger, it's 20% larger, or 20, it increases by 20%. So the lowest layer, it's the smallest increase, and the outer layer has the biggest increase,
Okay.
right?
Now tell me something I never understood why, let's say, the conductor in this case is discretized with triangles and the insulation is discretized with quasi-rectangles.
Okay. I mean, you mean,
Yeah, let's say, look at this, for example. The conductor here is discretized with triangles,
yeah.
which is it's a typical thing, right? But the moment you go to the first, let's say the first semicond, these triangles become squares or rectangles.
Oh, exactly. Okay, so this,
So is that controlled by you
that's
or
controlled by me, exactly. So I'm gonna show the difference. So this is why I use user control mesh, because I want a custom mesh, which means COMSOL has operations for you to choose to make efficient meshes, right? Depending on the geometry. If the geometry is symmetric, like a cylinder, right? The cylinder is symmetric, although that here I modified the cable surface to have contact with each other. So here it's flat. So it's not really a true cylinder, right? But it's cylindrical enough that I could apply an
yeah.
operation to distribute
Zoom in there,
elements.
please. Zoom in there, please, in where you put it flat, because this is very important. If
Yeah,
you guys see, as we approach two circles touching each other, at some point the triangle, I don't think my mouse would be visible, but as you
yeah,
see,
right here.
this triangle there it's becoming degenerate. The next one will be impossible. It will have a very small area. And if you remember, in all the final elements matrices, um, there is a division by the area, 1/4 times the area. So if this area is very small, you're magnifying the error. So in that case, instead of having the conductors touching at one point, it's best if we make these round surfaces that should touch each other to become a straight line. And then the problems with small area triangles disappear.
Exactly. So if I don't do this, then if it's just a point, right, in contact with a point connecting the two cylinders, there's gonna be a lot of curvature near that point, near that single contact point, and then we're gonna have degenerate elements, and then the mesh quality is gonna be below satisfactory, right? So once the mesh is built, I could right click mesh, I go to statistics, and you see here it says minimum element quality is 0.2095, right? So if I asked, I did research, I determined what is the minimum element quality, and online, or no, what I found out, minimum should be 0.1, so nothing less than 0.1. So this is 0.2095 because of this element, but near the contact between the two cylinders, right? Everywhere else should be greater. So if I clear this, see, outside from this region, see, it went to 0.3861. But as I get closer, see, it's 0.2095. So it really doesn't matter. Like this region in this case doesn't really matter because all the heat transfer is taking place in other areas outside of this central area.
Fayaz is asking for let's say the dead triangle in between the three conductors. What is that he's asking?
It's the same 0.0. All this around this region here.
There is a triangle between the three. That triangle that is in that
this one.
No.
What was the question?
No, my question is that is it the different material you are using in this, like the triangle, as well as the two conductors are connecting through some special type of structure or something? What should I say? There is just like a triangle between the conductors.
A triangle between the conductors.
No, the cables between the cables.
Sorry.
You mean this triangle here?
Yes.
Yeah. This one, as well as the conductors connected through some like different meshing.
This is the conductor here.
And then there is this is connected with the second conductor through some a different shape, not exactly the triangle. This one.
Okay. So this is the conductor. This is one layer, the conductor screen, right? So the different shapes, they have different shapes because I'm using a different mesh operation on this, right? Which is called here map, generate structured quadrilateral mesh. See, structured. When a mesh is structured, the mesh is you actually save on the number of elements, and the mesh is more efficient and has more quality, and it's easier. It allows the simulation to converge easier. So that's why I use this. So
no, Fayaz is asking about the lines that are thicker that are connecting conductor to conductor.
Here?
The thicker lines, yes. Yeah.
No, the previous ones.
I mean, these are just, I can control like how many divisions.
So, but you drew those lines, right? You drew the line.
I don't have to draw nothing because look, you see, I have all these operations here. I could say, I want for each, see, this is a separate arc, right? That curve, that's one curve. And that one curve, I want 18 divisions. So I could control how to divide every element, how to divide the,
okay, so but
arcs.
Here you chose to use, let's say, a semicircle there, but then you use, if you continue on rotation,
different
you use different arc lengths.
Exactly, different distribution numbers, and the reason is,
and that's the question for Fayaz has.
I just choose the appropriate number that when I check the statistics, I try to get the highest number. I try to get the highest
I see.
quality, right?
So you do this like this because you have a lot of experience and you know what it works and what it doesn't.
Exactly. Let's say I construct the mesh. I need to decide how to distribute, right? But a rule that I start with, I try to have a conductor, the cable service the conductor, the cable itself, right, is 360 degrees, right? I think
Yes.
the minimum, I think the maximum angle or on a cable, right? Or like 360 round, the maximum angle any sector should have is 15 degrees. I don't think we should go more than 15 degrees. I think it should be 10, like 5 degrees, right? So I try to be around like 5, no more, no more than, definitely not more than 15, but
Okay.
5
Now,
degrees, 10 degrees. So if we divide that 360, right, into 5, that I try to use that number to
okay. Now,
determine.
let me tell you, let me ask you a question.
So 90
If you don't do all this fancy meshing versus just let the program do the meshing, what will be the difference in convergence? Will I never get convergence with the standard meshing?
Okay,
Or
let's try. Look, build all statistics. How many elements I got here? 15,144, right?
That's okay.
Remember this number, 15,144. And quality is 0.2, right? Now I'm gonna go to physics control mesh. I'm just gonna let it build, right? Okay, now I'll do the same thing. Statistics. The minimum, look, it went from 0.2095, it went to 0.02, right? The number of elements, it went to half, but the quality dropped, right? So let's see, maybe what I gotta do, course, so maybe go to course. Let's see if I get it better. The number of elements are increasing, but the quality is not increasing, right?
what about if you do extremely fine?
Look what happened here. Over here it's
Yes. Oh, yes.
you don't have control. You don't have control of how the boundary layers are placed, right?
And those triangles are going to give you a lot of trouble.
Exactly. So this could be the reasons why you have convergence problems. But if I go back, see where it says boundary layer? I choose where to apply the boundary layers and where not to. So where you see highlighted blue, that's where I'm applying the boundary layers. And this is my boundary layer outline. So I'm applying it around this line here, this boundary, right? I don't want to apply boundary layers in here because this region is too small and it's too narrow and it's going to create low quality elements. I don't want that. So in this case, when I have total control, I have control of the quality, control of the number of elements. I could check the quality, right? Satisfactory, above 0.1, it's 0.2, even better. So now I can move on to the solver settings, right? Because now I have more confidence that it should converge, right? So once I have a good mesh, I can go to solver settings. And it's, like I said, the solver settings is not going to tell you to do your mesh good, right? You have to have a good mesh and you have to figure out for yourself that. The solver settings is ready for you.
Okay, so now let's say that we go with this, right? And you say you're going to use the what do you call it? The not segregated, the other one.
Fully coupled?
Fully coupled.
Oh, wait, before we talk about fully coupled, let's just talk about segregated. So segregated, like I said, it separates the physics, it solves it separately, and then it emerges them the results, right? Like step by step, and it's per iteration. Just like what I did my paper.
But I want to know what segregated is. Segregated is not a solution method. Segregated is just it's something that COMSOL calls segregated, but it's probably a numerical method. I don't know if it is GMRes, if this is what is it? Successive or relaxation. What is the method that is really mathematically speaking? Not segregated, it just means it's separated, right?
Okay.
But it's not the name of a solution or it's not the name of a method. So what is the method that is using? the numerical
I
method.
can talk to you more about fully coupled solver because that's what I use more, right? But
Okay, fully coupled, that's fine.
okay, but still, the generic name, segregated solver, generic, right? Whatever, like it doesn't have a mathematical name, but this is a type of solver that ANSYS uses, right? Because I did some research and I found out ANSYS doesn't have a fully coupled solver. They have a segregated solver, maybe something similar like this, right? But basically, you have a termination technique. So all these settings here is similar to the fully coupled, except the fully coupled has a few more settings, right? But we have a tolerance setting. So we could converge based on tolerance, or you want to stop the simulation based on number of iterations, or
I
both,
see.
right? We have a tolerance factor.
How does the tolerance factor affect the results?
Now this is like, if we have to take it like a flow chart, right? Flow chart, we have maybe like different loops, right?
Mhm.
You have different iteration, right, going on in the loop, right? So the stationary solver, I mean, yeah, in the stationary solver here, remember we talked about relative tolerance. It's gonna compare the current result with the previous iteration, right? The final result, right, at each iteration, right? And these are like, this is like an intermediate tolerance, like
Yeah, the intermediate iteration or something.
exactly, intermediate iteration. This I leave it default. I don't touch this. Usually I adjust the relative tolerance, because this is, especially in time dependent solvers, this is what controls the time step. Not in other words, if I go to time dependent solver, right? And it says output, see here, output times, and I have to select the time step. This is just the time step of when to output the results, not to calculate the result, right? So to control the time step when the result is calculated, not outputted, right? We have to adjust the relative tolerance. And then for a stationary solver, this is gonna control the results of when computed at each iteration, right? Or between iterations. So real quick, so this we have and then pseudo time stepping is a technique, like although there's a stationary solver, like time is independent, like time doesn't exist, right? But we still have something called pseudo time stepping to help with like with the model, will help solving the simulation, especially when there's time dependent effects or results that depend on time, even though this is stationary. But for example, like fluid flow, convection, stuff like that, this is doing something like behind the scenes to consider those effects that would be important in the stationary results. So, and then here is something I now, if you are you using the resources, everything in your computer, or are you using resources outside the computer, right? So if you're not using anything outside the computer, I turn this off. This is off. I turn it off. So you could be using like you may have different drives in your computer, right? Hard drives. So you need to, like, I like to keep my simulation running in the drive that the simulation is installed in, and not use any other resources. So I turn this off, and everything else I leave it as it is. Now we have solver settings, different types.
Okay,
Paradiso.
now,
Are you familiar with these?
no,
Well, they have different advantages, and like I said, this is for default. The COMSOL assigned this solver as default. They have different advantages and pros and cons, but for speed, Paradiso is good. It has like good robustness, but mumps is considered the most robust, but it takes a little longer. So if you want like good speed and good convergence, like I mean good robustness, Paradiso. But if you want more robustness, you don't mind waiting a little longer to get results, then you could switch to mumps. But like I said, we don't have to worry about this, just leave it default, right? Now, then going to fully coupled solver is what I use more often than anything. Here we could see the different types of solvers.
Okay, I know, I know what Paradiso is. It's an LU factorization.
Yeah.
So, yeah, that's what it says. It's an LU factorization.
Okay.
So what is the next of the other one?
You want to go back to the this thing?
Yeah, I want to know the names of the other solvers. Paradiso is LU. So
Okay.
it means it is based on almost getting the inverse of the matrix. So what is the name of the other one?
Mumps. And then spools. And dense matrix. I mean, I only use Paradiso and mumps. I haven't used other ones.
Mumps is an LU factorization.
So if I click this, we see.
No, mumps is
memory allocation factor. I don't recall like
okay.
the
Mumps
details.
Mumps is LU factorization, but uses pre-ordering algorithms and permutations to minimize the fill in.
I could
So it's very clear for me now what they are doing. So
no, I could go to help. Okay, that's another thing too. It's good that you asked this, because for anything that we have any questions about, we can right click anything and go to help. And as you see here, it's gonna bring up. Hold on a second. What is this? You see this help dialogue here?
I think mumps allows.
Hold on a second. I don't know why.
Mumps allows parallel.
Yeah. What was this? You see this yellow border? No. Okay. It went away. There was something in the way. It was strange. Okay. So mumps is multi-frontal, massively parallel sparse direct solver, the default. Paradiso parallel sparse direct solver. For more information, go to reference 2. For mumps, it estimates how much memory the unpivoted system requires. Enter memory allocation factor. I mean, there's a lot of details, a lot of information for any user to read and learn about. And it's quick, it's easily accessible. So is that just a one click away, right?
No, but it's clear to me what they're doing. They are doing LU factorization rather than relaxations. Basically, they are using getting the inverse of the matrix over solving the iteration using Gauss-Seidel.
Okay.
This is where I wanted to go. So of course, this is a lot more robust. Now, I don't see the more advanced methods. I don't see any from the Krylov subspace, because the LU cannot fully be parallelized. Cannot. So
okay, I could search anything. What was the names you said? I could search in the help and it could bring me to that location.
See if they do GM-res.
GM-RES?
Res, yes, like this. Yeah. If they do GM-res, those are the Krylov subs. Oh, they did this.
Yeah, they do it. Yeah.
The heat transfer interface is the linear default setting. Default linear solver is determined based on the number of degrees of freedom and physics interface settings. For small number of degrees of freedom, the direct Paradiso solver is used. It is known to be robust and fast for
There you
small
go.
size problems. Yeah.
Yeah.
For larger models, the linear iterative
Yes.
GMRS.
GMRest is absolutely the best for matrices that are symmetric, and they work by trying to guess the minimizing the GMRest is minimizing residual. I don't remember the G. Generalized minimization of the residual. So, and the idea is that they pre-multiply the matrix by the best guess of the inverse. But let me see. They also have MGRES, conjugate gradients, big stabilized. So it's a full package. It is really good.
I have seen these options in nonlinear solver settings.
Yeah.
FGMRES and these things, but they are not in the general solver settings. For the nonlinear solver settings, these options can be selected. FGMRES and these things.
Well, I'm happy they have them because these are the most advanced things. The Krylov subspace, all of them are Krylov subspace. And Krylov subspace is basically multiplying for your best next guess of the inverse of the matrix.
Okay, so once I added the fully coupled solver, it disabled segregated solver, right? So I could right click and enable it, and it's gonna disable the fully coupled solver, right? But as you see, the segregated solver doesn't use the GMRS solvers because it doesn't look like, right? Because
because GMRES is trying to solve the whole thing coupled.
exactly. So if I enable fully coupled solver, and then I could, so let me see. Let me go back. Wait, let me go back. What I did. Okay, I think it's based on here. So if I select,
So there are basically three ways to solve any matrix. One is by factorization, like LU. The other one is iteration, like Gauss-Seidel, the successive over relaxation. And the third one is Krylov subspace. So
okay. Yeah, you see these solvers here? AMG, GMG, AMG, they use GMRS. But this direct radiation does not use MOMS or parity. So, but
which is okay. I have no problem with LU factorization. The only thing is that you cannot really parallelize LU factorization. And GMRES, if you have multiple cores, multiple access, like, for example, the supercomputer, you can compute each one of those inverse matrices, which is, you're going to get to the solution by getting the inverse matrix. You're going to solve AX equals to B, and multiplying this for A0 to the -1, pre-multiplying this for A1 to the -1, and off you go. So, and at the end, when you get to the inverse, you have 1 multiplied by a chain of things. And vector matrix multiplications are the easiest thing to parallelize, right? Because vector matrix, right? You do matrix, vector, so it's one row at a time. So for the size of, if you have sufficient cores, if your matrix is 10,000 and you have 10,000 cores, it's like doing one operation. Yeah. So
yeah, and then
yes, is not understanding. I think I need to explain this. Let me take control of this. Stop sharing. I will go to this. I am not sharing, right?
Not yet.
Share the entire screen, share. Okay, I think I'm sharing now. I need to make this thing bigger. Okay. I don't have the pen. Give me a sec. So, solution methods. There could be more of what I'm saying, but in my experience, there is three only. LU, or let's call it factorization, which basically is Newton. The other one is iterations. Also, you could call it Gauss-Seidel. And the next one is the Krylov subspace. Okay, and this is mostly is based on residuals. It basically is matrix vector multiplication. Matrix vector multiplications. I am going to go very quickly on all others, but let's say the first one, factorization. So you have we are going to solve always we will solve the problem AX equals to B. Yeah. A may be constant if it comes from a linear problem. It may be not constant if it comes from a nonlinear problem. But let's start with the simple. So LU factorization, what it does is divides this matrix into L and U parts, triangular X equals to B. And then basically is a Newton elimination. Let me call it Newton elimination. So it's Newton elimination, and then you solve this by, there is an easy way to compute L and U by eliminating rows and columns. And at some point, you know, do the forward backwards. And I think everybody of you already knows this. Anybody has a problem? No. So this is number one. Number two is even easier, right? It's even easier because it's the iterations. Basically, if I were to A1X plus A2Y equals to B, and A11, A12, A21X plus A22Y equals to C, or let me call it B1, B2. So this thing tells you, let me actually do first the elimination. The elimination would see you come and multiply this matrix. You multiply this matrix by 1 by A11. You multiply this row by A11, and then you subtract it. You put minus that and add it. So you're going to have the equation below is going to have a A21, A11, and you need to make this number 0. So the next step, the matrix, the full equation is going to be A11X plus A12Y equals to B1, and then it's going to be 0 plus something here, which is A22 minus something that is 1 by A11, and there is another factor here, and the same over here, AY1, B2. So you get a 0 there. So at the end, when you finish with this, you just solve going things upwards. Now, the second method, iterations. So you have these equations, AY1, X1 plus A12, X2 equals to Y1, and A21, X1 plus A22, X2 equals to Y2. And from this equation, you get X1 equals to Y1 minus A12, X2 divided by A11. And from the other, you get X2 equals to Y2 minus A21, X1 divided by A22. And you iterate. So you say, first guess, Y is known. So you say iteration 0, and then you have this is iteration, let's say iteration I, and this one is iteration I plus 1. The same, this is I plus 1. And here you could do, if you do the better, A plus 1. So you do the Gauss cycle. So this is the iteration. Now, the Krylov, there are many methods for the Krylov, but these are the better one. Krylov subspace. So what we do here is you have AX equals to B. And based on the residual, so you say AX minus B equals to the residual. So what they try to do is, based on the value of the residual, and there are different methods to do this, based on the value of the residual, you pre-multiply AX equals B by a matrix that you call A0 minus 1. A0 minus 1 is normally called the preconditioner. A typical first guess on the preconditioner is if you get out of the matrix A, you get the A11, A22, blah, 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 A3, A and N. So you have all the other values, but what you do is, let me call it A0. So A0, you eliminate whatever is off diagonal, and you get A0 minus 1 will be simply 1 by A11, 1 by A22, so forth, 1 by A and N. And this matrix, the new matrix A, let's call this matrix, the new matrix A. This new matrix A, which now your system of equations has modified to A0 minus 1 A times X equals to A0 minus 1 B. And as you see here, you only need to do multiplications, vector matrix multiplications. So this matrix, this is a simple constant. So now, once this is preconditioned, so this is supposed to be, the values that you get here are supposed to be closer. So this matrix is what you want in the end. At the very end, so the end game is to compute A minus 1 multiplying times A, which will be the unity matrix multiplied by X equals to A minus 1 A B. And the A minus 1, you are going to compute it by a an iterative multiplications of a n to the minus 1, a n minus 1, blah, 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 to a1 to the minus 1, a0 to the minus 1, x, and the same thing, all these chain of multiplications there, times p. So this matrix becomes a unity, and the result gets directly obtained by a chain of multiplications. So this is what the concept is a bit complex, if you wish, but you keep on multiplying by your first guess on the inverse. For example, this would be a1 minus 1. And then you continue, a2 minus 1, until the residual is under a tolerance. So the residual is smaller than equals than your tolerance. And the beauty of this is that it can all be parallelized, because it's just, let's say, multiplication of matrix A by matrix A1 by matrix A2. Both, all of them are square. So you get the new matrix by multiplying, let's say, this row by this column and get this number. Now, then you continue going by this row by that column and get this number, right? And so forth. But each one of these things, so you multiply A1 here by this one, let's say, let me call it B. A1 by this value by this value, and then this value by this value. So you can use a different core for each one of these things, okay? And that is what makes it easy. That is what makes it fast. It looks a bit more complex, but vector matrix multiplication or matrix matrix multiplication is the easiest thing to parallelize. All right. That is my contribution to this. So, David,
Yeah, thank you very much.
Take over. Take over, please.
Okay. All right. Thank you very much for the lesson. So going back, so like I said, it's very easy to access help. Just right click on any node, right? Just click, right click, put help. The dialog pops up. You could search any term, and you could go directly to the information you're finding, right? Or the information you're looking for.
Mm-hmm.
So I'll close this for now. So the fully coupled solver, we have multiple options. One of them is automatic Newton, which adjusts the damping factor automatically. And the other option is that we use a fixed damping factor. So the damping factor is
But this is because you are solving, now you have a nonlinear problem. In your case, all what I described was a linear problem. So when you have a nonlinear problem, now you need to go into Newton and those things.
okay.
Yeah. So let me take over again, baby.
Okay, sure.
Let me take over again, just for a moment, to explain the nonlinear solution. I was going only with the linear. So let me share screen, share. Okay. Now, since David went the nonlinear way, I am going to go. This is all above. All this is for linear. Then there is a nonlinear. In electromagnetics, nonlinear basically only comes when you have magnetic saturation, hysteresis, and those things. If you don't have that, say you have anything with an air gap, like a motor, you don't really need what I'm going to cover now. But in general, when it's nonlinear, is that you're going to have to solve differential equations let's call them Maxwell equations, right? In the end, these are Maxwell equations. So you're going to solve something that has a derivative. Let me call it x dot equals to ax plus bu. And then you're going to have y equals to cx plus du. And this will be, this will come from Maxwell equations. But this matrix A is a function of x. This matrix C can be also be a function of x. So that is when the material properties are such that it's nonlinear. So you apply some integration method here to get xk plus 1 equals to a function of xk plus 1 plus uk plus 1 if you want, or uk fsk fk uk like this. And you get y k plus 1 will be just whatever matrix is. Yeah, let me change it. So y k plus 1 equals to let me leave it, let me call it g of xk plus uk. So no, commas, comma, and comma. All right. Now, because it's nonlinear, you need an iteration at every time step. No matter what, every time that you progress one time step, so when you go from x, let's say, change it to time. When you go from x t0 plus delta t, you're going to have to use this is going to be a function of x of t0, right? And the same, the g is going to be a function of this, like the g or your y, t0 plus delta t, even when this is not a function of time. But it's a function of the x, so it's going to be x of t0. And so you need to iterate there. So now you have differential equations and algebraic. Okay, how do you solve them? So there are 4 methods to solve them. The better one is implicit and simultaneous. You have implicit and alternate. You have explicit and simultaneous. And you have explicit and alternate. Okay, this is absolutely the most robust. The most robust. This will be the less robust, or the least. But this could be very fast. This is most robust, but I would even climb and say slow. And this is fast. And if they are giving you the same value, you go with the least robust. You don't care. So this is what you were saying, David. What is the topic that you put? What?
He was interpreting.
Was it nonlinear? It was Newton method.
Newton. So
Yeah.
So you get all this, you get all this equation, and you solve it with Newton.
Yeah.
Okay, so you solve Newton and you solve them at the same time, the differential equations with the algebraic equations. So that's what you do with the Newton. And Newton, you can go again. You're going to solve this matrix with LU. You're going to solve them with GMRes. You're going to solve them with everything, anything you want. Okay, but you use Newton, and Newton we all know it comes from a let's say y of x plus delta x comes from y of x plus let's call it a 0 plus a y prime x 0 delta x. So let me put it the other way around. Delta x. So you develop this in Taylor, delta x, y of x0 prime plus more stuff. We normally don't go into more stuff. Newton stops here, right? Newton uses only that, and this is some error, all of that. So, and that's how we solve for I'm missing here something. Delta x plus delta x plus some error. And what we want is to compute this. Delta x is the thing that we don't know here. So we're going to solve delta x. We're going to solve this for delta x until we compute it. If it's also a function of time, well, then the whole thing is coupled together and it's a big mess. Okay. So these are the methods. I stopped sharing, David.
In the nonlinear
Okay,
fill method is there.
Yes. Yeah.
thank you very much.
Okay. So show us more of the stuff in there.
Okay, so fully coupled solver, we have different nonlinear methods. On the method termination, automatic Newton automatically adjusts the damping factor. So what the damping factor does is for each solution at each data point, in this case stationary solver, at each iteration, it's gonna reduce the new value computed, right? So in other words, to not
Yes.
jump
So
too far ahead.
it's a deacceleration factor.
Yes.
Okay. So all right, it's fine. It's very good. This.
And yeah, so automatic will adjust that automatic, right? So we have an initial damping factor, minimum, right? All these settings. What is common?
They call it damping factor, but it's a
Deceleration.
deacceleration. Yeah.
Yeah, that's I guess.
In numerical method, we call it an acceleration, and in this case, it's deacceleration. Somehow they have known the experience that if you go during the iteration, the method is overshooting. So they say, instead of overshooting, let's reduce the amount of modification of that delta x. Okay.
Yeah.
All right. Keep on going.
So these settings here are relative to automatic Newton, but these settings here are common to the other Newton method, the constant Newton methods, right? So we have termination technique. We want to terminate based on tolerance. In other words, stop the simulation. Stop the iteration when a tolerance is satisfied, or we could use number of iterations. So here I'm using the maximum number of iterations, 25. So if an iteration is being run and it doesn't satisfy the convergence criterion, it's gonna stop and it's gonna give error. It's gonna say maximum number of iterations reached. If during the simulation, like the tolerance is satisfied and convergence criteria is satisfied, then it'll keep computing. It'll go to the next, compute the next iteration, the next in this case
time step probably.
Well, this is stationary, there's no time step. So if it's time dependent, you have a time step and iteration. Stationary is just iteration, right? So it's gonna keep computing. If it's no problem, it's converging, it'll just go to the next iteration or the next time step. If there's a problem, it'll keep trying, right? Using the damping factor, compute all the data
see.
at that point, keep computing, recompute, apply the damping factor, and if it still doesn't converge, it's gonna crash. It's gonna say sorry, maximum number of iterations reached. So for very complex problems, we may have to increase this. You know, it's very sad when you have a simulation running and you almost converge. You're like very close, like 80% to converge, and then at one iteration it says maximum number of iterations reached, and then it crashes. But if you had a few more iterations, it would have completed. So you may have to increase this a little bit. So then so a lot of time I use constant Newton method. So here,
constant Newton, it means that it's a constant Jacobian. Right? That's what it means. Is the Jacobian is constant. It's not like the Newton is constant. It's, in there, you say Jacobian update.
and then, I'm updating the Jacobian at every iteration. So what is constant, I think, is meaning the
click on every iteration.
I could choose every iteration on first
see.
iteration or minimal. Like, in other words,
So,
minimal.
so I don't understand. It makes no sense to me. There is constant Newton. What
Oh,
other?
the damping factor is constant. Remember I said?
No, but nonlinear method, constant Newton. So clicking there, and let me see what are the other options.
This is for.
So automatic Newton, the damping factor adjusts automatic. Constant Newton, the damping factor is fixed. It's not changing with the
simulation. I see. It refers to the damping factor.
Exactly. Yeah, this deceleration factor.
Okay, fine.
So here's
and the other is when you want to update the IC, when you update the Jacobian.
I always update every iteration. I a lot of times, most of the times, I try to use the settings that's the most complicated or the most to get the most accurate results.
But you have a big problem here because your convection is very highly nonlinear. So convection is extremely nonlinear. So whenever if you use anything that is constant, it's not going to converge. So you need to update it every iteration.
Yeah, exactly. So I always seek the settings.
But that is because of the physics that you are having in here. Yeah.
To be safe, right? To be safe, to avoid any errors.
It's slow, it's safe, but it may not be the most efficient way. Yeah, but it is safe.
It's accurate. So that's what I care about, accuracy and not have no surprises, right? So I check. I don't recall. Let me see. Oh, I think that that was the default setting, I think. Right? I didn't change this. That is what it is. So but if it was not, I would change it to every iteration, right? So again, all these other things here are similar. Now, one thing to keep in mind or to realize is that the default settings were applied to the default solver. In this case, it was segregated solver. See, tolerance factor is 0.1. I added the fully coupled solver, and then it appeared. But when you add a solver that's not the default, it will not have the default settings. So we saw that COMSOL used for the physics that I have, it used a tolerance factor of 0.1. So I should use also the default value 0.1. I should update this 0.1, right? So I need to update the settings that COMSOL used for the physics, right? The default settings. So I can update that at 0.1, and then again, stabilization, acceleration. This is a technique to facilitate convergence, especially when there's like fluid flow, in this case, convection. So I would choose pseudo time stepping, which is the same technique.
If you were to solve an electromagnetic problem which things are not here and which things are additional?
Everything I believe is here. I think
For an electromagnetic field problem, is the same thing?
I believe so. The only difference is that you have the option to enable it or not, right? Now, why would you enable like?
See if you can connect to this console.
So if we have electromagnetic problem, right? Why would we use pseudo time stepping or Anderson acceleration? Well, if we have like,
What is the Anderson acceleration?
let's read it from the manual because it will explain it better. So where is it saying? Wait, I think it's fully stabilization acceleration. Okay. Solution stabilization. Okay, pseudo time stepping. To use a pseudo time stepping method to stabilize convergence towards steady state for stationary solver. Pseudo time stepping is not available for time dependent solvers. For more information,
Anderson acceleration.
whenever there's let's say like diffusion, right? Diffusion. That's something that occurs in electromagnetics, right? Like we have eddy currents effects, right? Non-uniform current distribution. That's the diffusion problem, right? Like, so whenever we have stuff that has to do with diffusion, whether convection, like heat transfer, or eddy current effects, we need to, let me see. Wait, wait. It's okay. So AC, we're talking about AC, right? AC steady state, but it's still frequency dependent, right? You're still gonna have those ED effects, right? So those ED effects, even though the solver is steady state, it still takes into account the effects of like frequency, which is related to time, right? Time period, all that stuff. So it's solving a stationary model, and is using these techniques, pseudo time stepping techniques. But also Anderson acceleration is another option. So which is a nonlinear convergence acceleration method that uses information from previous known iterations to accelerate convergence. So Anderson acceleration method is primarily intended for acceleration of nonlinear iterations in transport problems.
I see.
Involving.
So it's something for heating, mass transfer.
Okay, see here, diffusion. So
but it's crosswind diffusion. It's not electromagnetic diffusion.
It is useful for solving linear or almost linear problems. Well, yeah, I mean,
I understand. No, this is not going to come in electromagnetics. This is going to come in thermal. Now, this is something for the Mexican people and all machine designers. There is no way to escape heat transfer problems when you are designing machines. The limits are always due to the heat. So you can design the most beautiful machine, and if it cannot take the duty cycle or the power that you want this to do because it overheats, it's of no use. So sooner or later, all machine designers need to do thermal analysis. Yeah, and Fayaz is just happy because he wants to do thermal analysis. Yeah. Okay.
I'm going to open up an electromagnetic model to see the settings.
Professor De Leon.
Yes, tell me, Fermin.
You allowed me to share our experience with this.
Yes, please.
No load currents. Not only to now that you're talking about the nonlinear methods, COMSOL, well, the support from COMSOL, they recommend two things to
So
have a
please,
convergence.
you want something to share, or it's just you're
Oh,
gonna?
well, no, it's, I think we can do it. I can only tell you what we are doing. The first thing that we are doing is in the elements, we are not using quadratic interpolation. They suggest to use linear. For this case of you remember that we are working in the no load current that is highly nonlinear, well, because of the BH curve of the core. So we are using first linear interpolation, and you can change that in the physics where you are using if you want, I can share my screen. Sorry,
Yes,
if
please.
you allow me
Yeah,
1 minute.
one second. See, here I opened up an electromagnetics model of the 2D generator.
Okay, you can open it. Yeah, please.
Yeah, you see this 2D generator?
No, we don't see it.
Oh,
No.
okay, hold on.
You are
a
not
second.
sharing the right
Yeah, okay,
screen.
yeah. Me go. Hold on 1 second. Now you see?
No,
Not yet.
now we see.
Yeah.
Okay. This is from the application library, right? So this is an example from COMSOL. We could go find any example, go on the top left click file, application library, and you can see all the examples available, right? So I just went to the AC/DC module, selected the 2D generator, and then I could show you the settings available that it has in the solver, right? So in the fully coupled solver, which it used by default.
By default.
By default, you use it fully coupled, right? Here is stabilization, acceleration. None is selected, but it's still available. It's there in case you want to use it, but it doesn't use it by default, but doesn't mean you can't use it. Like you may, I don't know. I mean, that's something we have to like look into and consider and see if there's any application in a 2D electromagnetics model. But and the same thing with the segregation.
But what is what you were going to say, Fermin?
Yes, well, it's about interpolation in the elements. Instead of using quadratic interpolation, they suggest us to use a linear interpolation.
We always use linear interpolation. I don't know who is using quadratic.
By default, is quadratic.
It's
I don't know if you allow me to share my
Yes,
computer. Let me show you here. You can see.
Yes, now it's here.
Here, do you see here in the physics? You can see here in discretization. You can use, by default, is quadratic.
Yes.
You can use even cubic, but by default, is quadratic. So you use linear, then they suggested us to use linear together with an improvement in the mesh to improve the conversion. But this was working very nice for us to change to linear and also improve the mesh, make it finer, the mesh. This was the first recommendation, and the second recommendation was to use in the time solver to use Paradiso, as you mentioned, and also here in a fully coupled, or let's sorry, let me show you where here in now. Where is it? Automatic. Well, there is another part where we have to change something. Is I can share you the
Time-dependent solver,
email.
maybe. In
Time-dependent solver.
Right there, maybe probably.
No,
But
it's
can you-
where you mentioned the Jacobian update every iteration. Also, they recommend that, and
Well,
it works
that's fully
very well.
coupled solver.
Yeah, that was
Now, Fermin, what is the problem that you're trying to solve here? We see a transformer. but-
yeah, it's the transformer, and we want to compute the no load current. You remember the
No
last
load current using the nonlinear model for
exactly
the core?
the nonlinear model
I
of
see.
the
I see.
core
That's
material.
why it's like this. Yes.
Yeah, it's highly nonlinear. Also, something that works very well for us is the highly nonlinear method. This one. This also work well for us. And but the one of the things that I think is good to try when you are using highly nonlinear methods problems is the interpolation, the discretization. Instead of quadratic, change it to linear. It will take maybe more time, and sometimes you need to improve the mesh, but it improve the conversion. We see that. So I am telling you this, Dr. Professor, because I will send to Fayaz this file with these changes.
This is a 3D model?
Yeah, it's a 3D model. Yeah, you can see here, it's half of the transformer, right? We are taking advantage of the symmetry to reduce the computational.
Yeah, now you need to be very careful with the symmetry.
Yeah,
with the symmetry boundaries. You need to be very careful.
Yeah. Do you know what we do first? We solve it in the frequency domain and we compute the impedance. Then when we see that the impedance is okay with this boundary condition, then we move to time domain. Yeah.
Now, is your core laminated?
Yeah, it's laminated, but no, we are not considering laminations. We are giving a constant conductivity, low constant conductivity. And we are considering that the current is mainly due to the magnetization, not due to losses also in the core.
Okay, all right.
Yeah. Sorry, it's only. Sorry, thank you for your time, Dr. Frost.
This transformer is very small, right? It's like
yeah, it's very small. It's
this should run in 5 minutes.
Yeah, but when it's not during the we consider the nonlinearity. And you know, when you're energized, also the inrush current, it will take some time. So we are. Let me show you. We are also something that is working well for us is to compute to apply voltages. Let me show you that they start in this way. No, it grow exponentially. So with that, we avoid the inrush current, and then we can see the steady state current after some few
This is
cycles.
very good. That's David uses a lot. We call it the ramping functions. Right?
Ramping functions, exactly.
Yes.
Yeah.
Yeah, but you know what? I realize for time-dependent studies or even the stationary, that if you reduce the relative tolerance, that avoids the necessity to use a ramping function. I don't use a ramping function no more.
Okay.
Because time-dependent study, if we control the initial time step, we can make the time step very small initially. That is then the solution is going to gradually increase the driving forces, excitation. If you have time step too big initially, then the excitation may be too strong to start the simulation. But that's why I said that in the time solver settings where it says output times, that time step has no effect on the actual time step. So let me see. Okay, so here you see if you click time dependent solver, right? A little lower, yeah, right there. Now see below time stepping, click a little, yeah, right there, time stepping, and you see right there initial time step. If you click this box and you make that time step small enough, you don't need you probably most likely, I gotta say guarantee, but most likely you won't need the ramping function.
Okay, it's a good suggestion. We will.
So that will depend, I guess, on the depending on what frequency you're using and stuff like that.
Yeah,
I still see that the time step is too big. I mean, you're
yeah,
saying
here we did it because the time, the computational time is very long. So we used to do something like that first, and then maybe we reduce it.
Okay.
We see that it's working.
Yeah.
What's I think
But give me just a moment. I don't see any inrush here.
Yeah, no, because, well, it is voltage. you're going to see.
Oh, I
Well,
see.
with this, we can avoid, with using this ramp, we can avoid inrush current.
Yeah,
Let
but
me see if,
I still want to see some non-linearity or some.
yeah, the non-linearity. I don't know if this problem is the last one that we have been solving, but let me see if currents, let me show you the currents right here. This is,
I see.
well, this is not a very nice simulation because you cannot see it, but you can see here the non-linearities that start to appear, no? The third harmonics and 5 harmonics.
Uh-huh.
But
I see.
because of the time step is very, very bad, it's very long, very large, we
Mhm.
saw all this type of response. But we have better simulations, yeah.
I
But
see.
we're, yeah, with this ramp step, we didn't see the inrush current. But if we don't, we apply directly the voltage, the full wave, then
Mhm.
we will see big current
Yeah.
here at the beginning in
Okay.
some of the phases, not in the tree, depending on what time is closing.
Can you show me? Can you show me your nonlinear model of the? Because there are many ways to model this thing, nonlinearity too.
Okay, well, if you want to see what the
So
BHQ,
you only have. I want to see the curve. You only have magnetizing. You don't have hysteresis. So that makes it a bit
no, is, well,
simpler.
this is the BH curve that we are using. This one.
And is that steep? When you get to the knee, then it goes at a mu zero, but you don't have another point in the middle.
Here in the,
Yeah,
here,
right
do you
there.
mean? Yeah, no, we don't have. You know, the COMSOL, they have some applications that you can, starting from the measurements, you can make it smoother, smooth this curve. I mean, these some applications that they have available in COMSOL. You can use the curve that you have maybe for measurements and put in this application, and they will give you a better curve with a smoother changes, no? And avoid
Now,
the,
tell me something. That slope, the slope of the last line, is that mu
that.
zero?
No, well, here you mean this?
No, no, the previous one.
This one, this
Yes.
part is, I don't remember, no, but it's not zero, no.
No, not zero, mu zero.
Mu zero, yeah,
Four
the
pi
slope,
10
yeah.
to the negative 7.
Yeah, it's the slope, it's the mu zero, yeah, right, you're right.
So what is the
I
red
mean, it's
thing?
mu.
What is the red thing?
This
At
word
the end of the
is
line.
extrapolation. You know, here you can, you see here interpolation and extrapolation. By default is, I think, is linear by default. They suggest to use constant extrapolation in these parts.
But then if you get there for any crazy reason,
yeah,
it's going to have an infinite current, right?
Yeah, because it's zero, yeah.
So
Maybe we have to
I'd
see.
like to change that and leave it. Yeah.
Maybe leave it like linear.
That would
Linear,
be
you
my
can see
preference.
now, if you put, sorry, you put linear, then you will have something different. See, it's not zero now.
I see.
You can see, you can change the slope, the permit. Here it's not zero yet. Yeah, maybe it's something that we have to check. But
fine, that's
yeah, here is not constant anymore.
no, it's increasing slowly, but that's a more physical way than just shave it off. It's like cutting a finger instead of let the nail grow.
Yeah. Okay, well.
Okay, very good.
I will send you to Fayaz later the file, Professor. You send me his email, and I will share with him the last file that we have been working with.
First thing, Fayaz, is you try to run it in your computer.
Okay.
First thing.
Yeah.
Then, if it runs, send it to the supercomputer.
Okay.
And as it is.
Okay.
And then you let me see, and we're going to reduce the time step. We're going to fine tune a little bit. You and I, this thing. We can all the time being have Fermin in the loop.
Yeah.
So
Thank
we
you.
exclude him from the loop.
Yeah.
Anybody else should be in the loop on this project? In Mexico. Fermin, anybody else we should copy with the results?
Yes, Paulina, but she's now in class. She's not here in
I see.
the meeting, but she was in
So
the
so
beginning.
I will send you the email of Fayaz, and then we connect. You put everybody else that should be involved in this, you put them, and then off we go. Now,
Yeah, thank you, Professor.
So I think the question started with linear interpolation and quadratic polarization. Like
no, yes. So that's for the elements. That's for the final elements method.
So which one is
Linear is what they suggest, and I'm okay with it. Linear is what we did. So
Yeah,
you take the values at the vertices.
yes, this is
For
what I have in
quadratic,
mind.
you get values in the middle of the lines.
Yes, this is what we know. And
Okay.
the cubic
Cubic, you get more values. Now you
more
need
values, yeah.
more values.
Yeah, this is in
And
my
the
mind.
idea of quadratic or cubic is that you can use larger elements.
Yeah, it's just like the
But-
more accurate the solution is, or the more robust.
More accurate, so that gives you the opportunity to use larger elements, fewer elements.
So it's not like related to some specific study or thing. It's just like the more
It
solutions.
depends on what kind of model you want for the final elements. You want linear interpolation, you want quadratic, cubic?
Yeah.
I don't think there is more than that. It's too complicated.
Okay. Okay, so the last thing we discussed is that constant Newton, and you said that constant Jacobian.
Yes.
Is it the same thing?
No, constant Newton seems to be, what was it, David? Because constant Newton means
Constant damping factor. Constant.
what's the damping factor?
It's the damping factor only.
So you make your next value, you normally
Yeah.
compute the next value, let's say xj equals to xj minus 1 times delta x, right?
So it's again
Plus delta x.
Jacobian plus something.
Delta x comes from the Jacobian. Delta x is Jacobian minus 1 delta v, let's say, right? So, but instead of doing this, you put here the acceleration factor some k. So constant Newton means k is equals to 1.
But my question is that in normally the problems we solve, there is a acceleration factor alpha.
Yes,
So, but
this
here
is the
why are
alpha. This is the alpha, but in this case, alpha is smaller than 1.
Why we are D is like a
Because apparently somebody knows that you overshoot. In most of our problems, let's say in Gauss-Seidel, successive over relaxation method, you always undershoot.
Yeah.
And then you use an acceleration factor to make you closer.
Yeah.
In Newton, you may overshoot. So if you overshoot, you're always going to exceed the value. So you want to go from this point to this point, and you get here. So you need to de-accelerate it, try to approach this. In Gauss-Seidel, we always know that you go in that direction, but never reach it. So you need to accelerate it. CS, you need to de-accelerate it. Okay? All right. What else do we have?
Well,
Do you have anything else, David?
Yeah, let me share the screen again, then let me see what
Yeah.
else to continue.
Paulina is there now.
All right,
Yes,
so
she's now here.
okay, welcome. So constant Newtons, we adjust the damping factor. For a stationary solver, you may have to damp it. You have to, you need to try and error, use different values. maybe 0.8, 0.7, 0.6. For time-dependent solver, I usually don't go below 0.9. I leave it 0.9 and do what I gotta do to make it converge, update the mesh, or something else. For a time-dependent solver, I think that if you need to use a depth effector like too small, I think then something wrong with the model. I think you're better off reevaluating the model, reevaluate boundary conditions and stuff like that. If that's the case. So again, similar to automatic knowing, we have a maximum number of iterations. You may have to increase this by a few iterations more, depending on the complexity of the physics. And all this is explained previous, right? And as I showed before, for the electromagnetics 2D generator model, the stabilization is not selected, but it's still available in case if you could.
But we are not seeing the electromagnetic, we are still seeing the thermal.
Yeah, because I closed it.
I see.
No, before I showed it, and I demonstrated that the default solver settings it used fully coupled, and it had stabilization acceleration not selected, but it was still there, right? It's still an option, you can still choose. That's pretty much me go to station. Me go to time dependence. It's time dependent. So as I mentioned before, we could apply the initial time step, check this box. You could apply initial time step based on the time, depending on the frequency. If you're using like frequency, what frequency are you using, right? So you want to divide the period of that cycle, or if you're not using frequency, if it's not AC, you still want to then for in my case heat transfer, there's something called time constant, right? Or even electrical circuit time constant, right? So you have an idea of what the time constant is, you want your time step to be much smaller than that time constant, right? So at least by 100. And then I would say that, yeah, maybe by 100 or 1,000, but you want to have a reference. You can't just use any time step, right? You have a reference with a time constant or period, and that's how you proceed.
Yes, that's very important. It's very important not to just simulate, but to do a good estimate of what the time constant is. Otherwise, you may be missing important information or having too many points in a particular simulation. So it's very important to have an idea of the time constants.
Yeah. And if you don't know what the time constant is, you can always run a preliminary simulation. Just run a simulation, see how it evolves, and then you could stop the simulation. You have an idea of what it is, right? And then you could update the initial time step.
So what you're saying is, if I have no idea, I don't know, why wouldn't I have an idea? It's a physical problem. I need to have an idea no matter what. Yeah. But I can be wrong by orders of magnitude, but I need to have an idea of what my time constant is going to be. Yeah. And if it is an LC circuit somewhere, you get the smallest L and the smallest C, and then that gives you the fastest transient, and then you get the largest C and the largest L, and it gives you the slowest transient, right? So that's what I would do to at least try to round it between something. Now, if
you have that information figured out, then use it. But if you don't have that data and you want like something like
but what I'm trying to say is that you should try to get it before you do all your simulation. You need to know what to expect.
Oh, okay. That's a very good point.
Yeah.
Check this out.
Yeah,
That's
you need to know
good.
what to expect of any simulation, because you will not know if it is right or wrong.
That's very good. That's very good.
In fact, I will always do a very simplified geometry first to see if things make sense. In fact, if I have an analytical solution for something, I will go for that analytical solution first. Reproduce it, and if it works well, then I complicate my life. But before that, I wouldn't complicate my life.
I mean,
Yeah.
that's true, especially when you're simulating a new type of model, right?
Yes, correct.
New
Yeah.
physics you're not familiar with. But once you have experience and you're familiar, then you could start more complicated. But definitely,
Yes, of course.
you
Yes.
start simple. Now this is why one of the reasons why I like COMSOL versus ANSYS, right? Here we have parameters, right, on the global definitions, and see, I could just basically compute my parameters, right? I could use expressions, units. It's gonna tell me if my units are correct, if they make sense. Now, with COMSOL, I could easily create a parameter and I could change the name. I could call this tau 8. I could rename it however I want. In ANSYS, once you create a parameter, you cannot change the name. You have
Okay,
to.
let me understand that. You are changing here parameter from tau 4 to tau 8.
Exactly.
Is it going to change it everywhere tau 4 is being used?
Yes.
Wow, that's pretty good.
I have all these parameters, right? Hold on. All these parameters. I could create one parameter list, and it's gonna use it everywhere because here's global. You see global definition?
Mhm.
Just like coding, MATLAB, whatever, C++, any language. You create a global parameter.
No, but if I'm coding and I use T4 or tau 4 down in the code,
Oh, but
it
yeah,
will
yeah, but
it
I'm
will
trying to
not
say
be
that.
redefined, and I will have a bug in there.
Yeah, but it's not order dependent. It's like the parameter is not depending on the order of the tree. Like I could define the parameter
like regular
here.
coding. I understand. Like
But you understand
regular
what I'm
coding,
saying? It's a global. It's
sequential.
yeah, it's
Yes.
global, right? With
Yeah.
ANSYS, once you create a parameter and you parameterize a model, right? And you parameterize the geometry. You create a geometry. You made your model adaptive. You could change dimensions. But let's say you really want to change one of the names of that parameter. You can. You have to delete it and recreate it. that to me, that's a disadvantage.
David, you would have been frustrated with the way I learned to program. Of course, I'm
Yeah.
the oldest person in the call, but I learned to program in the 1970s. And you needed to use, probably nobody was born in the 1970s, right? But you needed to use the memory allocation, okay? And it was a big mess because you sometimes needed to use, because there wasn't a lot of memory, the same allocation for different things. So it became a royal mess, we will say. But anyways, I'm very glad that you can do those things. It would have saved me hours of coding and debugging.
This is the benefit of living now. This time we have technology, right? We have
So,
options of which
not to call you
technology.
old, but that's too old, and I recognize it. But guess what, David? People who are five years older than me or more never learned to program.
Yeah,
Okay,
you made it.
my
Then.
generation was the first one that kind of learned to program and do things. Yeah.
So we could create parameters. Like I said, we could use the parameters. We could rename it, and we don't have to delete
Since
it.
you are giving all sorts of good things about COMSOL, tell me something bad.
Let me think about that. But okay, let's think. Can you think of something bad? Because I can tell you good things. Look,
I can think about the streamlines. The streamlines are not good. In ANSYS, they are much nicer.
well, boy, first of all, we have to
are
If you're talking about things from years ago compared to now, we need to look at things now, not a
So,
problem that
what you're telling me that you can see the streamlines and they look realistic, they are real? They fix that problem?
well, look, the bottom line is, I don't know, we need to look at it, right?
I started using COMSOL about 15 years ago,
All right, right. But this is my
before I
point.
used something else. ANSYS in particular was pretty good, but about 15, 16 years ago, I started using COMSOL, and I did electromagnetic problems, let's say the fields of a coil, and the streamlines were not right. And
I think it has to do with the user, the settings, and even if you call COMSOL, you speak with an application engineer, and COMSOL tells you that they don't have an answer.
And the COMSOL people told me that they don't have an answer.
All right, but
But that
that
was
doesn't
probably
mean.
15 years ago. So
All right, but hey, number one, it's 15 years ago. Number two, you may have to ask multiple application engineers because not everyone's gonna give you the same
I
answer.
see.
Right? It's
So
like
when
you
you
go to a doctor tells you one diagnosis, you go to another doctor to give you different diagnosis, and then the third doctor gives you the solution, right? So you can't really rely on just one
So
person.
what you're telling me is that in COMSOL support, there's different levels of expertise.
Just
and
like
you need
ANSYS.
your
Just like
question-
when I worked with ANSYS, we had, first of all, my job was to report bugs. My job was to help customers resolve issues and determine if it's a bug or not, right? I would look at the model, look at the simulation, and I would try to provide an answer, try to resolve the issue. If I was not able to, and not only me, other application engineers too, if we were not able to resolve the issue, we would have to escalate it higher in the ANSYS chain and let the developers give an answer whether it's a bug or not. And a lot of times they said yes, it's a bug, and just they'll fix it in the next version, it will be fixed, right? So so the bottom line is like no software is perfect, right? Completely, but from my experience, COMSOL is very good. No, I'm gonna tell you the main reason. Number one, multi-physics.
But
And
have you
it's
done any
one platform.
multiphysics?
Huh?
Have you done any multiphysics?
With ANSYS?
Yes. No. With COMSOL.
If I have done?
Yes.
All the time with heat transfer.
Oh, I see.
Heat transfer, solids, surface radiation, convection, that's multi-physics, multi heat
But
transfer.
for example, an electromagnetic field with a thermal.
Not with COMSOL, but I will be doing that soon. I mean, that's my plan is. So I want to do that. Because right now I have been using IEC equations almost all the time, right?
I see.
But I want to start doing
You do a single conductor, solid conductor, where you change the temperature of you change the resistance with temperature, and then you compute the temperature iteration, and the two things are combined, but in a full multiphysics, not in an equation.
No, full multiphysics, I know, yeah.
Yeah.
No,
yeah.
so okay, so
Yeah.
have you seen any problems with the?
No, I have seen people doing it.
No, I'm saying in COMSOL, like with the heat transfer physics, right? With the convection, have you seen anything with the fluid flow, streamlines, or like the field distribution, anything that looks weird or wrong? But everything looks good, right?
No. I think they fixed it, but you need to understand that I don't follow all the developments. I mean, when we started using COMSOL, and I was frustrated with the not being able to see the streamlines correctly, and then we went to ANSYS and I could see them very well. So at that point, we switched to ANSYS. Then they gave us ANSYS for free, so we double switched to ANSYS. And
All right,
then,
so I guess that's something
the students didn't like ANSYS, so we went back to COMSOL.
So we would have to then we have to look at the new version of COMSOL, see the updates with the streamlines, right? Electromagnetics, right? Flux lines, right? But let's talk like in general, like not that's 15 years ago. Let's talk about now, right? Most likely that problem is fixed, right?
Now I don't know. That
I'm-
I don't know. I've been seeing Fayase simulations. They look pretty good.
Okay, they look good. So let's assume everything's good, right?
The problem
Let's
is that
assume it's good, right? Now check this out.
3D visualization is still not exactly what I want. I'm probably too demanding. But I want to see 3D visualization and I want to cut the orange in different locations.
Okay,
different
what I
places.
did with the heat transfer with the forced convection tunnel model, right? I was able to cut the slices and show the
Like
different.
that is good. Like that is good, but I haven't seen it yet in electromagnetics.
You haven't asked me. I'm gonna do it now. You asked,
All right.
I'll do it. I'm gonna deliver it. But okay, let's assume that's good, right? Now, with COMSOL, we could do multi-physics. We could do heat transfer, electromagnetics, and if you want to add structure like vibrations,
Yeah, we're doing now
let's say we're doing a
vibrations
motor.
with
Let's say we're
we're
modeling a
doing
motor, right?
vibrations with Sikao. I don't know. Sikao is not here today.
Okay,
But
let's
we're
say
doing vibrations.
we're modeling a motor. We have heat generation, we have electromagnetic heat sources, right? We have heat transfer, we have vibration, so we need structures, mechanics. We're gonna need like 5 different physics, right? Because we have heat transfer, solids and fluids, surface radiation, we have convection, electromagnetics, that's 4, right? And then we have the coupling between those, right? In COMSOL, we do everything in one platform.
Yeah, one drawing.
One geometry. We create the geometry one time. We create the mesh one time. Everything one time, right? And everything's together. And we solve one time. Compared to ANSYS, you need, for each physics, you need a different software. You need to create the geometry each time in one software, unless you created one software and you have to export it to the other software. So there's a lot of exporting, a lot of transferring files and stuff like that. And then there's something called Workbench that connects all the physics together. So it, to me, very complicated, very annoying. And it's not free of bugs, because there's times that, you know, people report bugs. Hey, how come it's not working multi-physics? And it's sometimes as a consulting engineer, when a customer came to us for a project, the ANSYS team that was in, they avoided the multi-physics. Oh, it's going to be too complicated. Let's not do that. Let's simplify. Let's look for a simpler solution. Let's do things
Yes.
differently,
Yeah,
right?
yeah,
So
I
they don't
know.
want to do multi-physics. So like,
I know the multi-physics that we wanted to do with you and your company, it was never multi-physics.
right? They try to avoid it as much as possible. So like, all right, so hey, I got the experience with COMSOL. I had experience with ANSYS. Therefore, you know, at this point, to me, and COMSOL is a winner. So
Okay, David. Any comments from anybody? We are coming to the end, Fayaz. So it's a comment in general. What is your general comment?
Well, I just want to request David if he can share some more information regarding non-solver solution options, because I have seen some other names like FGM,
Non-solvers?
sorry, non-linear solvers. So it's F Grace or something, at different names other than parties or mums and schools.
Okay, tell me the names.
So my COMSOL is not like license issue is there, so I cannot. I forgot the exact names. It's FMG something, and then like different.
Those are all Krylov subspaces. Krylov subspace, they just come to the residual in a different way. So the most the best is GM-RES because it takes advantage of the symmetry. But if the matrix is not symmetric, you need to use the others methods. Okay. So all those on that list, those are methods to solve the same. It's similar to GM-RES, but for particularities. The matrices have different particularities, either being non-symmetric or have parts that vary versus parts that are constant. So there are different methods specific for one thing. Generic, the best one is GMRES. I can go with you on those methods one at a time.
Yeah.
I'm gonna tell you what. MATLAB has them all, and it has a very nice help. So you go to MATLAB and ask for the help on those things. They will give you even some theory about the methods. It's not going to be easy to read.
Yeah.
Okay. So, but anyways, you can give it a try. The most, I would say, robust is biconjugate gradient stabilized.
Yeah.
Yeah, big stab.
The BIC, it's
Big stab. Biconjugate gradient stabilized. That is.
yeah, this is also
Yes, that is the most generic, most whatever. Yeah.
Yeah.
And it's convenient. For example, when you're going to solve power flow using fast decouple, the metrics are not symmetric. So you can't use GMRES. I know you can use conjugate gradients either. So you go to biconjugate gradients, and the best thing is stabilized. I'm gonna give you a paper.
Okay.
All right. All right, guys. I don't know if we find some subject for next week. If not, we will talk about what Fayaz has a long list of things. Yeah, and if not, we talk at least on the solution from the Fermi's transformer. Okay.
And then we look at the streamlines.
And we look at the streamlines. So if you want to join next week, you're welcome, David. We've been meeting for about 3 months, every Tuesday at 1 New York City time. By the way, a warning for the Mexicans. David speaks in Spanish very well. Okay, he lives in Puerto Rico, so
very good.
Don't say anything bad. Okay.
Why would anyone say anything bad?
No, you never know. You never know. Why would you never know what people would
Why
say?
you give the warning for? Though? Why you give a warning? Though? I should be.
It's a warning. It's a warning that David has an Italian last name, but David is really David. His grandmother called him David, so it's
Yeah.
yes.
Okay.
Okay, guys. See you
Okay.
then.
See you. Thank you.
Thank you. Bye.
Bye bye.
Bye.
See you. Bye.
Thank you.